the last talk was rather practical and very beautiful, but now we will need to change gears, because my talk is rather theoretical. In fact, so much so that I was worried that I would not be able to publish it without inventing or fabricating some practical applications. So, but fortunately, a few months back, Kenta noticed that this work could be used to make a model of the quantum lambda calculus. And so, with that in hand, I decided to submit it to QPL, and here I am. So the next talk will be about this this application. So, but first, before I talk about the real content, let's talk about PhD students. So, as you know, when you encounter a PhD student, he's either sleeping or she's either sleeping or working, and this behavior is quite different from that of a full professor, which only works. Well, of course, this is not completely realistic, I know this. Actually, a PhD student also exhibits some undefined behavior. But anyway, this is an example of a substochastic map. And if you don't like this representation, using those multiple arrows, so it's not a real proper mathematical function, you can also write it as a mathematical function by mapping PhD to subdistribution. So the fact that these two things are basically the same can be, so these and these are basically the same, can be expressed like this. So stochastic map from a set X to a set Y is basically the same as an ordinary sharp map from X to the set of subdistributions on the Y. Now, if you want to compose these kinds of substochastic maps, one needs to know more structure of S. So S will be then monad, and then we can say that the category of sets and substochastic maps is isomorphic to the classic category of the subdistribution monad S. So in other words, substochastic maps are Kleisli maps. Now in this talk, I address the problem, what about quantum processes? Are they also Kleisli maps? Which means something like, if you have a quantum process from some data type E to a data type B, is there some sharp quantum process from A to the Q of B, where Q is an appropriately chosen monad? Well, of course, this is not really a precise question, because you need to define these notions and symbols. But I would say that if A and B and Q of B are restricted to only finite dimensions, as is done often, and I think for very good reasons, then the answer is no, unfortunately. However, if we relax this requirement and allow infinite dimensions, then the answer is yes, I would say. But this, of course, depends on the exact definitions. So let's go to these exact definitions. Let's start with something uncontroversial. I think that the finite dimensional quantum data type should be a ring of matrices. So I've put one example here. So these are the 2x2 complex matrices representing a qubit. These are the 3x3 complex matrices representing a qubit. These are pairs of complex numbers representing a classical bit. And the whole thing, the whole sum, represents a probabilistic combination of these three things. So, as you know, matrices can be added, multiplied. You can take the adjoint of a matrix. There is the identity matrix, also the zero matrix. So, a set of matrices is a ring if disclosed under all these operations. So, in particular, in this case, a ring is also closed under the star. So, maybe I should call it the unital star algebra. Anyway, if you want to go from the finite dimensional case to the infinite dimensional case, it is useful to note the following. Any ring of matrices, like this, is part of a full matrix algebra. And this, again, is isomorphic to the vector space of linear functions from C to the 7 to C to the 7. Now, to go from the finite to the infinite dimensional case, one simply replaces C7 by a Hilbert space. So I would say, perhaps more controversially, that a quantum data type is a von Neumann algebra. That is, it's a ring of bounded operators on some Hilbert space H. So this is the von Neumann algebra. which, in addition to being a ring, so closed under addition, multiplication, star, etc., should also be closed in a suitable topology. So actually the precise nature of the topology is very important, but not for this talk. I will say that this is only the smallest topology that makes all vector states continuous. But this is a polynomial algebra. Right. So now that we have our objects, let's also define the morphisms. So I denote by Vn CPSU the category for polynomial algebras and normal completely positive subunit maps. I don't have to explain to you what completely positive means. And normal is a requirement that has to do with the suitable topology, namely that the map should be continuous with respect to it. Maybe I do need to spend some words on subunital. Namely, maybe you would expect trace non-decreasing. However, for polynomial algebras, we don't in general have a finite trace, so we must make do with the unit, and then we take the opposite direction. So CPSU map from A to B is a quantum process from B to A. Well, so we also need a notion of sharp map, and this is even more contentious. I think a sharp map should be CPSU map, which is multiplicative and unitive. And I think these maps correspond to sharp quantum processes. Okay, so then the result is the following. The category of quantum processes, so the op is because it's in a different direction. The category of quantum processes is isomorphic, I claim, to the Kleisli category of monad from the category of sharp quantum processes. I'm afraid that I will not have time to show you the proof, but I can give you a proof sketch. It goes as follows. So first, the problem can be reduced to just showing that the inclusion of Vn into Vn CPSU has a left adjoint. That is because Vn and Vn CPSU have the same objects, and then with turning the wheels of diagrammatic reasoning. Oh, yes?
Can you remind me how we define sharp quantum processes?
Oh, well, so that is a
what is it?
unital map.
So what is it actually as a process?
Yes.
I mean, how is it different from other quantum processes?
It is difficult to say. Well, it preserves these operations of multiplication and so on, and so you can define, given a state, you can define like covariance. So if you have state phi, you can define the covariance of two operators A and B on phi to be the phi of A star B, and then a multiplicative maps preserve these covariances. So maybe that gives an idea. I don't know whether these sharp maps are actually used in.
Okay, good. I got the ideas.
But anyway, this seems like a natural thing. But I'm open to suggestion. Anyway, the proof sketch. So, so we need to prove that this is a left adjoint. And for this, I use the adjoint functor theorem, which reduces the problem to the following two things. The first task is to show that Vn has all limits, so the products are equalizers, and that the embedding preserves them. The second point, which is, I think the first point has the real mathematical content. The second point is more of a foundational issue, because when you try to prove the adjoint functor theorem, you form some huge products over with an index collection, and you want to know that this collection is in fact a set, otherwise you cannot form the product. So, so to make sure that this big product this big collection is indeed a set, this solution set condition was invented. And I think that maybe in a nominal founded setting, this thing might not be necessary. Anyhow, the interesting thing is that the real mathematical content, the number one, is actually the simplest to prove. Namely, to show that this is true when it simply figures out what are the products in the category of polynomial algebras and it shows that they are the same in Vn CPSU. The second point, which is more of a foundational issue, is actually requires more work, and it follows from the following observation. So, so suppose you have a polynomial algebra B generated by a set X, then I claim that the polynomial algebra B can be much larger than X, but not larger than 2 to the power such complex numbers times such X. And I don't mean the ordinal exponent, I mean the proper set function space exponent. So I've told you next to nothing about polynomial algebras, but still I think I can give you an intuition why this is reasonable. Namely, if you want to generate a polynomial algebra P from a set X, then what must you do? So remember that the polynomial algebra is a ring, so it should be closed under addition, multiplication, and other algebraic operations, and it should be closed in this suitable topology. So to generate polynomial algebra, we first add all the sums and products and stars, and after that add all the limits. So adding all these algebraic operations, well, it doesn't take much space. It's just complex numbers times C, because you need to add all the scalars. However, adding the limits is more difficult, because if you have so limits in this suitable topology, they are not just sequences. These limits are taken of nets, and a net might have an arbitrarily large index set, which is a problem. However, luckily somebody invented the notion of a filter and showed that any limit might also be taken, so limits can also be taken of filters, and this is sufficient. And a filter on the set y is no bigger than 2 to the power 2 to the power y, so that explains this part. Let's see, how much time do I still have left?
Well, you have 3 minutes.
Ah, okay. Well then, okay, you can ask now, nice, maybe it does exist, but what is it? Well, let me just say that on the 0 it's 0 because 0 is final and f preserves that. And the fc is actually more interesting. It's the set of continuous functions on the unit interval. Well, this is not quite right. I need to add an asterisk here. I'll explain why later. So to show that this is the case, we need to show that it is universal, and I think I'll skip the argument. But anyhow, this thing is not. So this is like the functional calculus for those in the know. But anyway, this thing is not a polynomial algebra, so I should add 2 stars. But I do want to say this. This thing, if you apply the left adjoint to just C, you get something that behaves like the polynomial algebra generated by one element. Then, if you want to figure out what f of c squared is, then this will be something like the polynomial algebra generated by 2 predicates, which will not be commutative. So describing this thing will be something like describing 2 non-commuting operators, how 2 non-commuting operators behave. And this seems like a very difficult problem. So I don't know what this is, but I do know that if one has a nice description of this thing, one will also have something like a spectral theory for non-normal operators, which seems dodgy. But anyhow, let me just mention an application, namely Kenta and I found a model of the quantum lambda calculus using this adjunction and a second adjunction. The second adjunction I also submitted, but this was rejected, unfortunately. Well, I think this one is more interesting anyhow. But but this will be the subject of the next talk. But let me just give you a teaser. Any questions?
No, it's all clear. One very quick question. That was not quick enough. Thank you again.